this lesson, we're going to look at proofs with algebra. Just like geometric proofs, algebraic proofs have to be laid out correctly, and they have to have a proof statement at the end. Let's take this example. First of all, we need to understand the three-line equal signs means that this is an identity. All an identity means is that the left-hand side of the identity sign equals the right-hand side for all values of n. So if we look at this identity, we could substitute n equals 2 into this identity, and we could show numerically that for n equals 2, this identity is true. However, all we've done here is demonstrated that it is true for n equals 2. We've not proved it's true for all values of n. In order to do this, we need to use algebra. So the first thing to realise is when we're constructing a proof, we don't ever write down both sides of the equals or identity sides, and we don't ever work on both sides at once. It's not like an equation where we're working on both sides doing the same to both sides. This is a common mistake with proof layouts. Instead, we start with one side only, usually the left-hand side, but it doesn't have to be. So we start with one side only, and we use algebraic manipulation to gradually change this side until we show that it equals the other side. So let's have a look at how this would look. So if we're starting with the left-hand side, we write LHS for left-hand side. Notice we don't write down the right-hand side at all. We completely ignore the right-hand side. We're just trying to manipulate the left-hand side to make it equal the right-hand side. So if we expand the brackets, now it's always a good idea because of this minus sign here to keep the expansion of n plus 3 squared in brackets. And then on the next line of working, take the brackets away and remember that this minus outside will change these two positives to a negative. And then if we simplify, we get n for n plus 16, which we can factorise, and then we can put equals the right-hand side at the end. And for this type of proof, this is in essence our proof statement, the fact that we've shown it equals the right-hand side. So let's just have a quick run through one more of those. So this is an identity proof. Again, we're going to work on one side only. Start on the left-hand side, write it down, expand it, taking care with the minus outside the brackets, simplify it. Now we haven't quite got what it looks like on the right-hand side, so I can see I need that plus 8 on the end. So I'm just going to separate that 12 into plus 4 and plus 8 to give me the plus 8 on the end, and then factorise the n squared plus 5n plus 4 into double brackets, and I get the right-hand side, so I put equals right-hand side at the end. Okay, so I'd like you to pause the video now and have a go at some of these identity proofs. So on the sheet, 1 Algebraic Proofs, GCSE, I either want you to do questions 3, 4 or 5, or 5, 6 and 7. Just have a look at this note here. If you're doing 6 and 7, it's actually easiest to factorise into a single bracket rather than expand everything out. If you're not sure, you can have a quick look at the solutions at the end of the document. So pause the video and do those now. Okay, now we're going to have a look at a proof where you're asked to prove or show that an expression is a multiple of a certain number. So with these proofs, we expand the brackets and then we try and refactorise the expression we've got so we have that number we want it to be a multiple of outside the brackets. Let's have a look at this example. So expand the brackets, take care with that minus outside the brackets, simplify. So we can see this gets 12n. So for our proof statement, we want to show it's a multiple of 6. So we can write 12n as 2 times 6n, and we can say hence a multiple of 6, and this is our proof statement. Just go back to that one a second before we move on. I just want you to choose 2 questions to do now. So go back to the same sheet, and from questions 8 to 12, just to choose 2 questions where we're showing that an expression is a multiple of a certain number. Pause the video and do those now. Okay, now we're going to look at how we show that an expression is not a multiple of a certain number. So here we're going to expand and simplify the brackets as usual, factorise with the number we want to show it's not a multiple of outside the brackets, and show that we have something extra added or subtracted on the end. So let's just see what that looks like. So we're proving this expression is not a multiple of 8. So we're going to expand everything again and simplify, taking care with the signs because we've got the minus outside the bracket. And we get 8n minus 10. So what we can do here is we can factorise 8n minus 10 by taking out a factor of 8, but we can't take out a factor of 8 of the 10. So we could actually just pop in another line of working in here. So 8n minus 10 I could write as 8n minus 8 minus 2, and then you can see there that I've factorised the 8n minus 8 by taking an 8 outside, and then I've got the minus 2 on the end. And then our proof statement would say something like 8 brackets n minus 1 is a multiple of 8, so 8 brackets n minus 1 minus 2 is not a multiple of 8. We can also use this idea of factorising with a plus or a minus at the end to show that something has a remainder when it's divided by a number. So if, for example, we'd expanded everything, simplified it, and we'd managed to factorise it so that we had 6 outside the brackets, n plus 3, and then a plus 5 at the end, we could show that our expression is divisible by 6, because the 6 outside the brackets here shows we're divisible by 6. With a remainder of 5, the plus 5 would be a remainder. Okay, I want you to have a go now at question 14 on the sheet, so pause the video and try that one. Okay, another type of proof is we can be asked to show that an expression is always even or always odd. So again, the expression that we're given, we can expand and simplify it. For example, if we'd ended up with 6n minus 2, we could take a factor of 2 out, and then we could write a proof statement saying it's divisible by 2, hence always even. If we wanted to show that something was always odd, again, we would expand and simplify the expression. And then we can see here I've got 8n minus 1. So I can show that 8n is divisible by 2 by showing that that's 2 times by 4n. So we could either write the 2 brackets 4n, or in here alternatively we could just put that 8n is 2 times 4n. So we can say 8n is divisible by 2. So 8n is always even. Therefore 8n minus 1 must be odd. Again, there's our proof statement. An alternative way that we could show that something is always even is that we can use these facts written here on the left. So let's apply those to this example, explain why n brackets n plus 1 is always even. Well, let's consider both scenarios. If n was an odd number, n plus 1 would have to be an even number. So you'd have an odd number times an even number, which is always even. Conversely, if we started with n as an even number, n plus 1 must be an odd number, and again, even times odd is even. Okay, I'd like you to have a go now at questions 15 and 16. Pause the video and try those. Okay, the last type of proof we're going to look at is when we're not actually given the expression, the algebraic expression we're starting with. We're given a worded question and we have to create the algebraic expression ourselves. So we need to look at how we write certain things algebraically. So first of all, consecutive numbers. If we're asked for consecutive numbers, we can write a series of consecutive numbers. We can start at n, and then we could just carry on n plus 1, n plus 2 for as many consecutive numbers as we need. An even number, if we take an integer, if n is an integer, if we multiply it by 2, it doesn't matter if n started off as odd or n started off as even, 2n will always be an even number. So to define an even number, we would start with 2n. If we wanted consecutive even numbers, 2n could be our first even number. The next even number would be 2 along, so it would be 2n plus 2. If we needed a third consecutive even number, it would be 2n plus 4, and so on. If we, however, are asked for two different even numbers, so they're not consecutive numbers, so if, for example, we could have 6 and we could have 32, then we need to use two different letters. So two different even numbers, we'd have to say 2n and 2m. Okay, so look at the difference here. When we're working with consecutive numbers, we do it all in terms of n. When we've got two completely different even numbers, we're using different letters, 2n and 2m. Let's look then at odd numbers. So if 2n is always an even number, 2n plus 1 is always an odd number. So consecutive odd numbers, we'd have to start with our first odd number as 2n plus 1. So the next one would be 2 along for that, which is 2n plus 3, and we could keep going. If we needed another one, it would be 2n plus 5, and so on. Again, if we wanted different odd numbers, so for example 13 and 35, again we need to use different letters. So we'd use 2n plus 1 and 2m plus 1. Okay, let's just have a look at an example of one of these. So prove algebraically that the sum of the squares of any two consecutive even numbers is always a multiple of 4. So this time we need to write down the algebraic statement. So the sum of the squares of two consecutive even numbers. So we take our consecutive even numbers, 2n and 2n plus 1. We need to know how to write those. And we square them and we sum them, which means we add them together. Okay, take care when you're squaring these. 2n squared is 4n squared. Then expand the double bracket. Then we can simplify. Then, as before, take out a factor of 4 and write a proof statement divisible by 4, hence always a multiple of 4. Okay, I now want you to complete questions 20 to 24 on the sheet. All the model solutions are there, so you can mark them or come back to me if you're not sure about anything. Pause the video and try those now.